Hi everyone, and welcome back to What's Up Physics. My name is Aishwarya, and today we're going to be going over Newton's first law, second law, and how to draw free body diagrams. Oops. Alright, so we're going to first start with systems. What is a system? A system is an object or collection of objects being treated as a single unit. So for example, let's say we have these three boxes over here, and a force pushes all three of them collectively, which is this applied force right here. Instead of just analyzing each individual box's motion, we might want to analyze the motion of the boxes together as a whole, as if these boxes were one object. For example, instead of finding the net force on each individual box, which is actually different for each box, what if we wanted to find the force that is being applied to this unit, or all three boxes as a whole? We might say that FA, or this applied force, is the net force on the system of boxes. And also this is because the vertical forces cancel out our normal force and gravity, so our horizontal force, or this applied force on the box, on our unit, is going to be our net force. Now, objects don't necessarily have to be touching if we want to consider them a system. For example, we have these two cars over here. They're not touching each other or enacting forces on each other, and they aren't really related to one another. But we might want to consider them as part of one system to look at a force that's acting on them collectively, like the force of, say, a tractor beam that's pulling them both up. Which, don't take the tractor beam force seriously, but the idea makes sense. However, we do sometimes look to analyze how two objects are interacting with one another or affecting one another within a system. Forces within a system, or forces between two objects inside the same system, are called internal forces. Forces that act on a system as a whole, like the tractor beam or the applied force on the three boxes, are called external forces. It's a little abstract in theory, so let's go over some examples. Okay, so first we have a person system. This only includes the person and nothing else, so the gravitational force applied to the girl by the Earth is an external force to the system. Next, we have the person-Earth system. This time, the Earth is included in our system. So, forces such as the gravitational force the Earth applies to the girl and the applied force of the girl's weight on the Earth are both internal forces to our system. Now we have a pencil person-Earth system. Any forces between the girl and the Earth are internal, as well as any forces between the girl and the pencil. If the girl uses applied force to push the pencil around or anything, that's internal. Even if the girl were to drop the pencil, the force that it would apply to the Earth and the gravitational force pulling the pencil down would both be internal because both objects are part of the system. And finally, we have a person-pencil system. Forces between the pencil and the girl are internal, but once again, the gravitational force is an external force because the Earth is no longer part of the system. So if the girl were to drop the pencil this time, the applied force of the pencil on the Earth and the gravitational force of the Earth on the pencil are both external forces. Alright, so here's one last example of a system that is super important for this unit. This is called an Atwood's machine. It's basically just a pulley system. A string passes through the pulley with two weights or blocks on either end. Now, let's define all the forces present in this situation. To start off, we have the gravitational force acting on the two boxes. One is greater than the other because this box over here has a greater mass, so it's going to have a greater weight. Now, we also have the tension force in the string pulling up on the boxes because the boxes are hanging from the string. Now, real quick side note, don't get confused. Although I'm drawing two tension vectors on the machine, there's only one value or amount of tension in the string, assuming this is an ideal string. We can't have two different amounts of tension in the string. That's not possible. I'm drawing two vectors because a singular tension force in the string is applied at 2 points on the two different boxes. Now, think about this for a moment. Which of these forces are external and which of these forces are internal to the box's string system? Okay, so let's talk about external forces first. The gravity forces on both boxes are external to the system because they are not exerted by an object that is defined as part of our system. Basically, we know that gravity is exerted by the Earth. Since our system is comprised of just the boxes in the string and not the Earth, we can't count gravity as an internal force. Now, what is internal to the system? Our tension string is internal to the system's motion. This is because we've defined the string as part of our system, so the tension forces it enacts on the boxes are also within the system and therefore internal. Now, let's think about if we're looking at just one of the boxes as our system instead of the whole pulley as our system. So let's take just the left box. If just the left box was our system, then both the gravity force as well as the tension force would be external. This is because the string is no longer defined as part of our system, so any force that it enacts on the box is no longer internal. And now this is the same as if the right box was our system. Alright, so the last thing I want to talk about is acceleration. If a system of objects is connected, like here in the Atwood machines, how the two boxes are connected by the string, then its parts must have the same acceleration as the system as a whole. This is just a fact, because both boxes will move at the same speeds at all times. So they'll speed up and slow down together, basically meaning that they'll have the same acceleration. Even if we were talking about a system that looked like this, let's say we have like 3 boxes connected by a string and they're all being pulled, or the other example we've seen of maybe a box sitting on a table and there's a pulley here and this box is falling. Something like this, any system like this, all the boxes would have the same acceleration because they're all connected. Okay, so now we're going to talk about Newton's laws. And for a bit of background, Isaac Newton was a physicist who created these 3 laws of motion, and they're going to be super important for Physics 1. Okay, so Newton's first law, or it's also called the law of inertia sometimes. It states, if the net force exerted on a system is 0 newtons, then the velocity of that system will stay constant. Or, in more common terms, an object will not change its motion unless an external, unbalanced force acts on it. Objects in motion will stay in that same motion, and objects at rest will stay at rest. Now, what do I mean by an unbalanced external force? Well, let's take this box sitting on the ground here as an example. The gravitational force acting on the box is an external force, sure, because the Earth is not part of our system right now. But that doesn't automatically mean the object's motion will change. Why? Because the normal force of the ground pushing back up on this box is equal in magnitude in Fg and therefore balances out the gravitational force. This cancels out gravity's effect on the object. An example of an unbalanced external force is if, let's say, a person applies a force onto this box. This applied force here isn't balanced out by anything else and so is able to affect the motion of the box by making it start moving. So you might have heard me mention earlier that the first law is also called the law of inertia. Inertia is the resistance to change in motion that anything with mass has. Basically, objects want to continue what they're doing, whether that is moving at a constant speed or staying at rest, which is why the first law is referred to as the law of inertia. The only thing that can change this continued motion, again, is an external force acting on an object. Here are a few examples of inertia. So for example, when you're in a car and it suddenly brakes, you get thrown forward before stopping. Why? Because the inertia in our bodies makes us want to keep moving the way we were previously before the brakes hit, which was forward. Momentarily, we continue this motion before the external force of the seatbelt restraining us makes us come to a rest. And for our second example, we're going to switch to a video demo real quick. Okay, so for the purpose of this example, we're going to take something reasonably heavy. I'm using this protein shake. Then we're going to put it on something light and easy to pull. I'm going to use a sheet of paper. Now, the idea is, if I put the protein shake on top of the paper and pull the paper hard enough, the protein shake won't move. So let's try this. Ready? 3, 2, 1. And obviously, the protein shake did move just a little, but in a perfect world where I pulled hard enough, it wouldn't move at all. Even in this case, it barely moved from its original place, and it definitely didn't move with the paper. Why is that? Well, the science behind this experiment is inertia. When I pull the paper super slowly, like this, the friction between it and the shake is an external force such that it causes the shake to move. However, when I pull the paper super quickly, like this, the friction is easily overcome. In other words, the external force acting on the shake is minimal enough that the inertia of the shake allows it to stay almost at rest. The heavier an object is, the more inertia or resistance to change in motion it has, which is why this experiment wouldn't work with an object like a feather. Now, this is a relatively simple experiment that you can try at home to understand how inertia works. Since I don't want to break any glassware, my experiment is also done with very simple objects. However, you should check out the Spangler Science TV video we have linked in the description box. They do the same experiment, but with a tablecloth and glasses stacked on top of each other. It's a much cooler version to watch. Okay, we're back. And I want to think about this idea now. What if you push an object? For example, if you try pushing your phone across your desk, while you're pushing it, the phone will move. But once you stop pushing it, or when you're no longer in contact with the phone, it'll almost instantly stop moving. Try it for a second. Aside from your initial applied force to push the object, you aren't applying any other forces to the object. So why does it come to rest instead of continuing on moving forever? That's because there is actually an external unbalanced force acting on the object, friction. If friction didn't exist, or was negligible, which is a key term in AP language, then the phone would have continued on sliding at a constant speed forever, or at least until the end of your desk, even when you stopped pushing because of inertia. Okay, so here I have a FBD simulation open to demonstrate this concept to you guys. So in this world, there is no friction between the wheels of the skateboard and the ground. So when the orange man over here pushes on this box and then lets go, it's going to continue moving at this constant velocity forever. Again, this is because of an inertia. Since there's no external force acting on the box, it's going to continue in this same motion forever. But if we head over to this tab over here where there is friction, and then we have our orange man push on this box again, I'm going to wait for it to gain some momentum. Okay, as we can see, the box is slowing down in its motion. And this is because the frictional force is now a net external force that's acting on the box. So it can't continue in its same motion forever. It's going to slow down and inevitably come to rest. But if we go back to this tab over here, that box is still just traveling at that constant motion forever. So for the purpose of this video, we're not really going to talk about friction in our practice problems. We're going to pretend it's negligible, which is that College Board key term for pretending it just doesn't exist. And that's because we're throwing a lot of information at you guys right now, and we want to keep it relatively simple. But in videos later on, we're going to add back in friction. And one last side note, this FBD simulation is really helpful and informative. So if you guys want to check it out, I'll have it linked in the description box. Okay, so now we're going to talk about a system's motion when its forces aren't balanced. This is where second law comes into help. So Newton's second law states that the net force on a system is equal to the mass of that system times its acceleration. This law is pretty simple and self-explanatory. It's basically just an equation we can use to analyze the motion of systems. But let's talk about what net force is. So net force is basically the sum of all the forces acting on an object. We sum the forces in each dimension respectively. So for example, let's say we have a box here that's sitting on a table, and we want to find its net force. Let's say that it weighs 1 Newton, so that's the Fg, and it's 1 Newton. And then the table is pushing back up on this box with an equal but opposite force. So this normal force over here is going to be 1 Newton but up. Now, to find the net force on this box, we want to sum these forces. So let's see. F net is equal to the normal force of 1 Newton. Now, for the gravity force, we want to subtract this from the normal force, because technically it's negative, since it's actually pointing downwards. So we're going to say 1 Newton minus 1 Newton is equal to 0 Newtons. So this box has 0 net force acting on it. Or in other words, there's no net force acting on it. Now let's say that there's an applied force pushing this box to the right with a force of 15 Newtons. And then there's a frictional force acting to the left of the box, which is 10 Newtons. Now, if we wanted to find the net force of this box, we already know that the vertical forces are balanced. Sorry, this normal force looks a little long. I just drew it badly. But the vertical forces are balanced, our horizontal forces are not. Let's take this 15 Newtons that's acting to the right, and then we want to subtract the 10 Newtons, because technically it's negative since it's acting to the left of the box. And that gives us a net force of 5 Newtons. Before we move on, there's a few more key ideas with regards to second law. The first is the direction of net force. All forces are vector quantities. They have a direction, which is just the direction that the force is exerted. So for example, if we have a box here, and it's being pushed, this applied force is positive, or it's acting to the right. If we have a tension force that's pulling this box, this tension force is going to be negative, or it points to the left. Net force is also a vector quantity. If the net sum of the forces exerted on an object is positive, then the net force points to the right, and vice versa. So for example, if we take our box here, and we say the applied force is a magnitude of 10 newtons and the tension is a magnitude of 15, then the net force on this object is going to point to the left, because 10 minus 15 yields negative 5, which is pointing to the left. Now, if we take a look at our second law equation, we can see that it's a vector quantity, acceleration, multiplied by a scalar quantity, mass. The result is a vector quantity, net force, that points in the same direction as acceleration. That is a key thing to remember. F-net and acceleration always point in the same direction. Finally, the last important thing to mention is the units for second law. We know that in AP Physics 1, acceleration is always measured in meters per second squared. The new idea is that mass is going to be in kilograms always, and force is always going to be in newtons. This is very, very important to keep in mind. When doing your calculations, your units must always be in kg, newtons, and meters per second squared. If you're trying to calculate the net force on the object, and you multiply its acceleration in meters per second squared with its mass in a unit like grams, then your answer will not be in newtons. So always watch out and make sure to convert your newtons to what they should be. If you're given a problem with a mass in grams, make sure you convert that to kilograms. Okay, so now we're going to take a break and learn how to draw free body diagrams, which is something Mariah is going to teach you guys.
Hey guys, Mariah here. Before we can get to solving problems about first and second law, we first need to learn how to draw free body diagrams. These diagrams make it easier to visualize the scenario and to find the net force acting on the object. How to draw a free body diagram. We'll be using the example of a ball that is falling at terminal velocity. The first thing you want to do is to draw the object. On the AP exam, they're going to give you a dot that represents the object that they want you to draw on. But it's often easier to understand the scenario when you draw the objects themselves, so that's what we'll usually be doing in our videos. Apart from that, we'll be following the rest of the guidelines. The next thing you want to do is to determine all acting forces. Just like how with kinematics you would only consider the object's motion in the scenario, while drawing FBDs, only include the forces that are currently acting on the object. When an object is in terminal velocity, there are only two forces acting on it, the gravitational force and drag forces from the air, or air resistance. Let's draw the force of gravity that is acting on the object. We know it points downwards, but where should our vectors start? Would it look like this? Well, on the AP exam, you need to draw vectors that point away from the object. You also should not draw force components. To demonstrate this, we'll use last video's example of a little boy pulling a wagon. If we were to draw an FBD of the wagon, we'd have to include the applied force that the boy is exerting on the wagon. And we're just going to represent the wagon at this point here. Since the boy pulls the wagon at an angle, the applied force vector would be drawn at that same angle. And this means that it has a vertical component and a horizontal component. On the AP exam, you should just draw the applied force without showing its components. However, drawing the components can really help you visualize the scenario and figure out the net force, so feel free to draw your own FBD with components off to the side. We'll be drawing components as dashed lines to help distinguish them from the actual forces. Force vector length and direction should represent the force's magnitude and direction. We know that when an object is at its terminal velocity, the gravitational force and drag forces are equal. So, those vectors should be the same size. The gravitational force should point downward because that's the direction the Earth would pull the ball, and since air resistance opposes the direction of motion, it should point upward. So, is this correct? Well, the College Board says that you should leave no space between the object and the vector. The vectors must touch the object, so you draw the vectors like this. Lastly, if multiple forces are acting on the object in the same direction, draw them next to each other, not overlapping. Let's say that we're pulling a kite straight downwards. The kite experiences the gravitational force from the Earth and air resistance. It also experiences a tension force going downwards because we're pulling the kite down with a string. We would draw the tension force and the gravitational force next to each other since they both point in the same direction, like so. Example number 1. Montana jumps horizontally from a cliff into the ocean below, experiencing no air resistance. Draw an FBD of Montana after she leaves the cliff. Montana starts with some initial horizontal velocity and has no initial vertical velocity, but since she is traveling downwards, she will gain vertical velocity. You can probably recognize that this makes her a projectile. Montana obviously has the gravitational force acting on her. That's what causes her to move downwards. But what force is causing her to move towards the right? The answer is no force. Montana is not accelerating horizontally, and according to the equation the net force is equal to the mass times the acceleration, we know that she would have to be accelerating horizontally to have a net horizontal force. But then why is she moving horizontally? When Montana jumped off the cliff, she pushed on the ground and the ground pushed back, causing her to move horizontally. However, since no horizontal forces act on her while she's in the air, she cannot accelerate horizontally and so will maintain her horizontal speed. We know this to be true because of Newton's first law. Objects in motion maintain their motion unless acted upon by an external force. Drawing a horizontal force here is a pretty common mistake, so when you're drawing your FBDs, be sure to consider whether the object's motion is the result of a current or a past force. Example number 2. Libby is standing on the scale in her bathroom. Draw an FBD of the scale. Firstly, since the scale is on Earth, Earth's gravitational force is acting on it. Libby also applies a force on the scale that is equal to her weight. Since Libby weighs more than the scale and the gravitational force is equal to the scale's weight, Libby's applied force is greater than the gravitational force. The scale will remain stationary when Libby stands on it, so the downward forces must be equal to the upward forces, otherwise it'd accelerate into the Earth. This means that the ground must apply a normal force to the scale that is equal in magnitude to the gravitational force and Libby's force combined. You might be confused on how the normal force could change based on which downward forces are applied on an object. But remember, both an ant and an elephant can stand on the ground thanks to the normal force, which is smaller for the ant and larger for the elephant, because they have smaller and larger gravitational forces acting on them respectively. It's just the same with the scale. When the downward force acting on it is bigger, because the force of Libby is also pushing down on it, in addition to that gravitational force acting on it, the normal force acting on it also gets bigger. And you might be wondering why it's the normal force that changes to keep the net force at 0 instead of the gravitational force. The gravitational force is equal to an object's weight in newtons, and given the equation that your weight is equal to your mass times the acceleration of gravity, we know this can't change unless you chop off a limb or you go to a different planet. Example number 3. A pumpkin is being pushed towards the right with a constant velocity. Draw an FBD of the pumpkin. The pumpkin is not moving vertically, and so it has no vertical net force. So, the gravitational force and the normal force are equal. Since the pumpkin is moving at a constant velocity, it cannot be accelerating. According to the equation, the net force is equal to the mass times the acceleration. If the acceleration is 0, the net force must also be 0. But if the pumpkin is being pushed towards the right, then it would have a net force. The only way for it to travel at a constant velocity while having a force act on it towards the right would be if a force equal in magnitude would act on it towards the left. The only other object that's touching the pumpkin is the ground. The force that the ground exerts on an object to oppose the object's motion is friction. So our FBD would look like this. Example number 4. A sled is going down a frictionless incline. Draw an FBD of the sled. If you've already seen our Intro to Forces video, then you've already seen us solve this problem. You can use the timestamps in the description box, just skip to the next one. We know that the sled is going to move this way. We also know that gravity is what will cause the sled to move down the incline. Does that mean that the gravitational force will act on the sled in this direction? No. As was stated in the last video, the gravitational force will always act downwards, towards the center of the Earth. But then how can gravity be causing the sled to go down the hill? Well, when a surface is inclined, our x-axis will be aligned with the path along which our object is moving, and the y-axis must always be perpendicular to the x-axis. So because the surface that the sled is on is tilted at an angle, this causes the axes to tilt at that same angle. Now you can see that the gravitational force has an x component and a y component. We can see that the x component of the gravitational force points down the incline, and so that's what will cause the sled to go downhill. But won't this unbalanced y component of Fg cause the sled to sink into the incline? No, because the incline will apply a normal force to the sled that is equal in magnitude but opposite in direction to Fgy. Now, you might need to find the values of these components in some problems. How can you do that? Well, the x and y components combine to form the resultant force, Fg, and altogether these three form a right triangle. And this right triangle is similar to the incline, so that the angle of the incline is the same as the angle opposite the x component. So if you know the value of f sub g, you can do this to find f sub gx. You can say that the sine of theta is equal to the opposite, which is fgx, over the hypotenuse, which is fg. You can rearrange to get that f sub g sub x is equal to f sub g times the sine of that angle. And then for fg sub y, you can say that the cosine of theta is equal to the adjacent, which is fg sub y, over the hypotenuse, f sub g. You can rearrange to get that f sub g sub y is equal to f sub g times the cosine of that angle, theta. Example number 5. A cow is being suspended in the air by a horizontal cable to the left and a cable 45 degrees above the horizontal to the right. Ow, poor cow. Draw the cow's FBD. Obviously, the force of gravity is acting on the cow. That's always the one that you should draw the first. We know that the tension force always acts in the direction that the cable is pulled. We also know that the cow is stationary, so the net force is 0. This means that all vertical components and forces and all horizontal components and forces must balance. Let's first draw this tension force from the cable to the left. I'll label it as F sub T1 to differentiate it from the other tension force. We have an unbalanced force acting downward and an unbalanced force acting leftward. This means that the vertical and horizontal components of the second tension force must equal the gravitational force and the first tension force respectively. I'd also like to mention that since the second tension force is 45 degrees above the horizontal, using special trigonometry rules, we know that the horizontal and vertical components are equal. This makes the first tension force and the gravitational force equal. Example number 6. A big block of mass big M is attached to a smaller block of mass little m by a string. A student attaches a string to the block of mass big M and pulls everything to the right along a rough surface. Both blocks travel at a constant velocity. Draw force diagrams for the blocks separately. Both blocks travel at the same constant velocity, so they both have net forces of 0 newtons. Since there is no net force on the blocks, the vertical forces must be balanced, meaning that the gravitational forces and the normal forces must be equal in magnitude. The block with mass little m will have a smaller gravitational and normal force acting on it because it has less mass. And this keyword rough tells us that friction is present, so both blocks will have friction acting on them. Do both blocks have the same amount of friction acting on them, or is one block acted on by a greater frictional force? Well, we know that the frictional force is equal to the coefficient of friction times the normal force, and since both blocks travel on the same surfaces, their moves would be the same. So the frictional forces acting on them are dependent on the normal forces. Looking at our FBDs, you can see that a larger normal force is applied on the block of mass big M, so it would have a larger friction force acting on it too. Lastly, we have to draw the tension forces acting on the blocks. The big block applies the tension force on the small block towards the right, and friction acts towards the left. Since the net force must be 0, the lengths of these vectors must be equal. The tension forces that the blocks apply to each other must be equal in magnitude because they are connected by the same string. So the tension force on the big block that acts towards the left looks like this. And since the net force must be 0, the tension force acting on this block towards the right must have the same length as the other two vectors combined. That's all for this lesson on FBDs. So now Aishwarya will be taking you through some practice problems on first and second law. See you later!
Alright, it's Aishwarya again. I know you guys missed me. And we're going to be going over example problems now and applying our newfound knowledge of FBDs. Okay, example number 1. Mariah is pushing a stroller with a force of 155 newtons at an angle 30 degrees below the horizontal. If the stroller is 50 kgs, what is the acceleration of the stroller? Assume no friction. Okay, let's start by drawing a picture of lovely Mariah over here with her lovely bangs. And she's going to be pushing this stroller downwards at an angle of 30 degrees. And then this is her applied force right here. Okay, so let's turn this into an FBD. We can draw our dot here. Immediately, we know that the stroller is experiencing gravitational force. And this force of Mariah pushing in. And we're going to label it FA, applied force. Excuse me. So we can immediately split this into components. Here's our horizontal component, and then here's our vertical. Now, we know the ground is pushing up on Mariah, so we can draw a normal force. But what's the problem with drawing our normal force like this, equaling the magnitude of gravity? The problem is that our vertical forces are unbalanced. Pointing down is the magnitude of Fg plus Fay, and pointing up is the magnitude of Fn. This can't be right. This means we'd have a net force pointing down in the vertical direction, or meaning we'd be accelerating into the ground, moving vertically. We know that's not happening in real life. If we go out and push a stroller or a lawnmower on the sidewalk, we're not accelerating into the ground. We only move horizontally. So if we're not accelerating vertically, we can't have a net force in the vertical direction. This means our normal force must make up for or balance out the downwards pointing vertical forces. So our normal force is going to look something like this. It's got to be the addition of Fg and Fay. Maybe it should be just a little longer. Something like that. And now this makes sense conceptually too. Let's say an object is just sitting at rest on the ground. So the ground, to combat the object's weight, pushes up with the normal force that's equal to the object's weight, right? But let's say you take your hand and you push that box into the ground more. You apply more force onto it. To make sure that the box doesn't accelerate downwards, the ground is going to be pushing up at an increased normal force to make up for the box's weight, plus your hand pushing down extra on the box. So basically, the takeaway from this problem is that the normal force can be greater or even less than the gravity force, which we'll see in our next problem. They're not always going to be equal. Okay, so now let's take this and let's solve the actual problem. We're looking for the acceleration of the stroller, and we already know its mass. So what we need to find is the net force on the stroller. Now, we just talked about how the stroller is only moving horizontally. Its vertical forces are balanced. So this horizontal component of Mariah's applied force is going to be our net force. I'm going to pull this triangle out over here so it's a little easier to see. And we're going to have to use some right triangle trick to find this net force, or this Fax. We know that Mariah is pushing with an angle of 30 degrees below the horizontal, so that's 30 degrees. And we know that this applied force over here, or the hypotenuse, is equal to 155 newtons. So we can say that cos 30 is going to be equal to our net force over 155, or 155 cos 30 equals Fax, and this is going to equal approximately 134 newtons. So now we have our F net over here, so we can use our second law to find our answer. I'm going to erase this ink. Okay, so we have F net equals MA. We just found out that our F net is 134 newtons, is equal to our mass, 50 kg, times our acceleration, A. And so we know that 134 divided by 50 is equal to A, which is going to equal 2.68 meters per second. Don't forget those units. Okay, example number 2. Mariah is now pulling a wagon with force of 500 newtons at an angle 30 degrees above the horizontal. If the wagon weighs 400 newtons, because Mariah built, what is the acceleration of the wagon? Assume no friction. Okay, let's start by just drawing our free body diagram. So the wagon weighs some force because of gravitational force, and it's being pulled up by the tension force. And so basically this scenario is just the opposite of the previous one. So we can split this into components. We have FTX over here and FTY over here. Now, what's the problem with drawing our normal force as equal to our gravity force again? So if we drew our normal force as equal to gravity, then our wagon would accelerate up into the air because vertical forces would be unbalanced. We'd have Fn and FTY pointing up and Fg pointing down. So we'd have a net vertical force up that way. So our Fn is going to balance out our vertical forces again by being smaller than in magnitude than our Fg this time. And more specifically, it needs to be equal to the magnitude of FTY subtracted from Fg, in order to make our net force vertically 0. And this makes sense conceptually because since Mariah is pulling up on the wagon at an angle, it's going to be weighing down on the ground less. So the ground doesn't need to push up on the wagon as much to keep it from accelerating into the ground. And therefore, our normal force is going to be smaller. Okay, so now let's solve this problem. Again, we're trying to find the acceleration of the wagon, which means we need to find our net force. And our net force is going to be Ftx because all of our vertical forces are balanced. We know that this angle of the pull is 30 degrees. So again, we can just use some trick to solve this problem. Cos 30 is going to be equal to the adjacent side of the triangle, so Ftx over the hypotenuse. Now we know that Ft is going to be equal to 500 newtons because we were given that that's the force she pulls the wagon up with. So we have that Ftx is equal to 500 cos 30, which is equal to about 433 newtons. And this is our net force. So now we can use second law to solve for our problem. We have 433 is equal to. Now here's where we need to be really smart and not make silly mistakes. So they gave us that the wagon weighs 400 newtons. This is not the mass of the wagon. Again, this is not the mass of the wagon. This is the weight of the wagon or the gravitational force acting on it. If we remember, Fg is equal to mg. So since our weight is 400, our mass is going to be m times, and then g is 10 on Earth. So our mass is going to be 400 divided by 10. And this is just a really good thing to remember. On Earth, if you're trying to go between mass to weight, you either multiply it by 10, or in this case, we're going to divide by 10 to get our mass. So our mass is going to be 40, and then we're trying to find acceleration. So that equals to 433 divided by 40, which equals to 10.8 meters per second squared. Okay, example number 3. Two blocks, block A of mass 5 kg and block B of mass 3.5 kg, are connected by a light string. The string is passed over a pulley with negligible mass and friction. A. What is the acceleration of the system of boxes when the masses are released and can move? Okay, so let's review some key terms first. So first of all, light string means that we ignore the mass of the string or that it's negligible, which makes sense because they didn't even give us that measurement. Now, negligible mass and friction basically mean that the pulley in no way slows down the acceleration of the system with friction force or anything else like that. Okay, so we're finding the acceleration of the system, right? And we were given the mass of the system because we have the mass of the two boxes, so we could just add that together. So basically, we need to find the net force to be able to find the acceleration. So let's draw the forces on our picture over here. And for now, we're only going to draw the forces external to the system. Why? Because only these forces affect the acceleration of the system as a whole. So we know that our external forces are going to be the weights of these two boxes. And since A has a greater mass, it's going to have a greater weight. So I'm going to draw that arrow bigger than box B's weight. So now, we know that the only two external forces acting on the system are the weights of these blocks. Even though the weights point in the same direction, which is down, they would cause the system to move in very different ways when it's released. So if A's weight was greater, which it is in this case, A would move down and B would move up. But if B's weight was greater, A would move up and B would move down. So we can see that these forces are actually opposing each other's motion. This means that to find the net force, we'd want to subtract their weights. So since block A does have the greater weight, we need to subtract block B's weight from it to find the net force. So let's start solving that. F net is equal to the gravity force on A minus the one on B, which that is equal to, let's see, we are given the mass of each, so A is 5 kilograms, times 10, the acceleration due to gravity, minus 3.5 times 10, and this gives us a net force of 15 newtons. So let's come over here. We know that F net is equal to MA, so 15 is equal to the mass of the system, which is 5 plus 3.5 times A. And this gives our acceleration as 1.76 meters per second squared. Okay. Part B. What is the tension in the string? Okay, so now we're going to draw on our internal tension forces. The tension in the string is constant throughout, so we're going to have arrows of the same magnitude pulling up on both boxes. And I'm going to draw that in right now. There's one tension force, and there's another tension force. Whoops, this might need to be a little bigger. Okay, so they should be roughly the same length and size. Okay, now remember, the acceleration of this whole system is equal to the acceleration of its individual parts, because it's all connected. Box A and box B both are also going to have an individual acceleration of 1.76 meters per second squared. Okay, so what we want to do now to find the tension is isolate one of the boxes and just look at the individual forces acting on it. And remember, this is because tension force is internal to the system of boxes, but it's not internal if we look at an individual box as our system. Then the tension force is a part of the net force that acts on each box individually. Now, we know both boxes' acceleration and mass, so we can find the net force acting on each box. The net force on each individual box also depends on the tension force pulling it up and force of gravity pulling it down. So let me show you what this means. Let's take box B, for example. We know that it accelerates upwards, so that must mean that the tension force acting on box B is greater than the gravity force pulling it down. Or in other words, F net on box B must equal to the tension on it minus its weight. Now, we also know its mass and its acceleration, so we can set these two equations equal to each other, and since we know the box's weight too, we only have one unknown, which is the tension force, so we can solve for that. Now, this method also would work if we isolated box A. The only difference is the tension force would be less than gravity. In other words, F net would equal to Fg minus Ft. Now, why is this? This is because we know that when the system is released, box A accelerates downwards. And so for its F net to point downwards, Fg must be greater than Ft. Otherwise, it would accelerate up. So we can use either of these scenarios to solve for the tension force. They both give us the same answer, but I'm just going to take box B's over here and use that to solve. So the Ft minus Fg, which this is the F net. Sorry, that was a really horrible curly brace. And that's going to equal to MA. All right, so we don't know Ft. We know Fg of box B is going to be 3.5, its mass times 10. And then we know that its mass is 3.5, and its acceleration, oops, I'm running out of space, is 1.76. So if we do the math, we get that Ft is equal to 3.5 times 1.76 plus 35, which that is equal to 41.16 newtons. Sorry, if we're going to do this in 3 sig figs, that's going to be 41.2 newtons. Example number 4. 2 boxes are hung, connected by a massless string. The string is passed over a pulley that is on a smooth incline, as pictured below. When released, which way does the system move, and what is the system's acceleration? Okay, so again, remember, smooth is a keyword for frictionless, so we're going to completely disregard friction in this problem. So we're looking for the system's acceleration. This means that the tension, it can be discounted because it's an internal force to the system and doesn't affect the whole system's acceleration. So to see which way the box moves, we want to compare the gravitational forces on the two boxes to figure out which box has the greatest force exerted on it. Be careful though. This doesn't necessarily mean just comparing the weight of the two boxes like our last problem. I'll show you what I mean by drawing the forces onto the boxes. So for this 4.0 kg box, it's pretty simple. It's just a line downwards for gravity. Now for the 5.7 box, let's draw that gravity down. It's going to be bigger than this one because it has a greater mass. And let's go ahead and split this into components. Sorry, that's a really bad straight line. So that's FGY, and this is FGX. And remember, this angle over here is 30 degrees, or the angle of the incline of the slope. Now the problem is that the normal force of the slope on the box is going to cancel out our FGY. So the only force that's impacting the 5.7 kg box is the horizontal component of gravity. So this means is that we're going to have to compare the weight of the 4.0 kg box with this FGX to see which is greater to figure out which way the system moves. So we know that the force of gravity, or the weight, on this box is just going to be 4.0 times 10, or 40 newtons. For this one, remember FGX is always equal to the weight sine 30. So the weight of this box is going to be 5.7 times 10, or just 57 newtons, sine 30. And this is going to give us 28.5 newtons. Okay, so the force on the 4.0 kg box is greater than the force on the 5.7 kg box. That means that the 4 kg box will move downwards and cause the 5.7 kg box to move to the right, like this. Therefore, the system of boxes is going to move to the right. Okay, now to find the acceleration of the system, we just need its FNet, and we already have the two forces that are going to impact our whole system. And so we're just going to subtract this 28.5 from this 40 newtons to find our net force. So FNet is equal to 40 minus 28.5. And now this is going to equal the mass of the system times its acceleration. I'm just going to write this down here so I have more space. Is equal to the mass of the system, which is 5.7 plus 4 times its acceleration. So once we isolate for A and solve, that's going to give us 1.19 meters per second squared. Yay! Alright, that's the end of the content section for this video. If you want to try your hand at some first and second law practice problems, be sure to go to part 2, which is linked in the description box. As always, if you find our videos helpful, please consider liking, sharing, or subscribing. See you at part 2.